Okay, so the mind map on homeostasis, let's try and remember everything, brainstorm, remember everything we know about homeostasis when it comes to physiology. So, homeostasis is the process by which the body maintains a stable internal environment despite external changes. And it's very, very essential for optimal cellular function and survival. So, its significance is basically in maintaining variables such as temperature, pH, electrolyte balance, blood glucose levels within narrow limits or a range. And this is very crucial for normal operation of cells and organs. So the fundamental components of homeostatic systems are receptors dealing with the afferent system, with the integration centers and effectors with the efferent system. Okay, so when we talk about the receptors or sensors, their role is to detect changes or stimuli in the internal environment. For example, thermoreceptors in the skin and hypothalamus for temperature, chemoreceptors in blood vessels for pH and oxygen levels, and integrating centers um, that has to do with the centers that process incoming signals from the receptors and determine the appropriate response. And with the location, it's primarily in the central nervous system. For example, the hypothalamus and the brainstem, and some reflexes are integrated at the spinal cord level. With effectors, um, actually, their role has to do with carrying out the commands from the integrating center to adjust the internal environment. And there are several types: the muscles contract or relax, shivering for heat production. When it comes to glands, secrete hormones or sweat, and the blood vessels constrict or dilate to regulate blood pressure and heat loss. And with the feedback mechanisms, when it comes to homeostasis, there's a negative feedback loop and a positive feedback loop. The main concept with when it comes to negative feedback loop has to do with the mechanism that reverses a change in the controlled variable, thereby restoring homeostasis. So the process has to do with four steps: deviation, detection, response, and correction. With the deviation, there's a variable, always a variable, which is, for example, body temperature. When it deviates from its set point, there's a detection where receptors sense the deviation, and there's a response. The integrating center sends signals to effectors, and there's a correction where the effectors act to counter the change. So examples are thermoregulation, where sweating occurs to cool down when overheated, and shivering to generate heat when cold. And also glucose regulation, where insulin release, lowering blood glucose when the levels are very high. With a positive feedback, and the concept is simple. So it's a mechanism that amplifies a change rather than reversing it. So the process, there are two steps: initiation and amplification. So a small change triggers a response, and amplification occurs where the response increases the original change. For example, in childbirth, where uterine contractions intensify as labor progresses, and also in blood clotting, where platelets aggregation accelerates the clot formation. Right, so let's look at some key variables and their regulation. In temperature regulation, I think of sensors, integrating center, and effectors. With the sensors, thermoreceptors in the skin and the hypothalamus in the integrating center has to do with the hypothalamus, and with effectors, sweat glands, which increases evaporation for cooling, and then skeletal muscles, shivering increases heat production, with the blood vessels, vasodilation, and or vasoconstriction to modulate heat loss. When it comes to blood glucose, the sensors has to do with the pancreatic beta cells, um, that is in high glucose levels, they're being they secrete insulin, and the alpha cells are the sensors. When it comes to low glucose, red glucagon is being produced in the integrating centers has to do with the central nervous system and also the pancreas. And the effectors are insulin and glucagon. Sensors, pancreatic beta cells and alpha cells, integrating centers, central nervous system, and the pancreas, and effectors insulin and glucagon. So the insulin lowers the blood glucose by enhancing cellular uptake, whilst the glucagon raises the blood glucose by stimulating glycogenolysis and gluconeogenesis. When it comes to blood pressure, the sensors are the baroreceptors located in the carotid sinus and the aortic arch, and the integrating centers are the brainstem, the medulla oblongata, and the effectors are the heart, blood vessels, and the kidney. With the heart, adjust the cardiac output. The blood vessels, they adjust the diameter through vasoconstriction or dilation. And the kidney, they regulates the blood volume via the renin-angiotensin or aldosterone system. So with the pH regulation, the mechanism is simple: buffer system, respiratory system, and the renal system. With the buffer system, bicarbonates buffering in the blood respiratory system, it adjusts the carbon dioxide levels via breathing rates. And with the renal system, excretes or retain hydrogen ions and bicarbonates. Okay, so another thing that we can look at is the integration of neural and endocrine systems. So with the neural control, you can think of speed and pathway. So with the speed, there's rapid responses via the autonomic nervous system, and with the pathways, reflex arc. For example, the baroreceptors reflex that involve intermediate adjustment, and the endocrine control, this one too, when it comes to speed, there are slower responses due to hormone synthesis and release, and with the mechanisms, the hormones act on target organs to modify their function, and their feedback loops, often negative, which adjust the hormone levels. So with synergy between the systems, we have the coordination, and many homeostatic processes involve both the neural and the hormonal inputs. For example, the stress responses. So redundancy and overlapping ensure that one system is impaired and the other one partially compensates. When it comes to molecular and cellular mechanisms, signal transduction, gene expression, and ion channel regulations are very, very important over here. So for signal transduction, receptor ligand interaction initiates cascade involving second messengers, for example, the cyclic AMP and calcium. But when it comes to gene expression, there's prolonged changes in the homeostatic conditions which can lead to altered gene expression to adapt to new steady states. And when it comes to ion channel regulation, the changes in the membrane potential in the ion influx or flux help regulate the cell excitability and function. With a clinical correlation and pathophysiology, knowing that you have to know that when it comes to homeostatic imbalance, it's very, very dangerous, as disruption in homeostasis can lead to several disease states like diabetes mellitus, failure in glucose homeostasis, hypertension, that's inadequate regulation of the blood pressure, fever, a reset in the temperature set points during infection. I can think of therapeutic interventions. Treatments often aim to restore or mimic normal homeostatic controls like insulin therapy, antihypertensives, and understanding these mechanisms is crucial for the development of targeted therapies. So, in summary, let's look at the key concepts: the set point, negative feedback loop, positive feedback loop, allostasis, and system interconnectivity. So the set point, that's the target value around which a regulated variable is maintained. Negative feedback loop, that is the primary mechanism for maintaining homeostasis. Positive feedback as a mechanism used in specific physiological situations to drive processes to completion. Allostasis, that's the process by which the body achieves stability through change. Emphasizes adaptation over strict consistency or constancy. And when it comes to system interconnectivity, the homeostasis is maintained by complex interconnections between neural, endocrine, and cellular mechanisms. All right, so it's good to be able to look at some case studies diagrams and flow charts about these loops, and also some of the integration with other topics like immune responses and stress physiology. So that's it for homeostasis.